All right. So here we go. We're going to finish up section 3.4 by looking at this practice problem. And the practice problem just says predict which proton, the red or the blue, is more acidic in each of these compounds. And since the title of the slide is qualifying, right, we're going to use the whole aereo, we're going to use the aereo concept to try to answer these problems, right? We have atom, resonance, induction, and orbital. Okay, let's start with A. If we look at the two hydrogens there, the red one and the blue one, you can see that those two hydrogens are both attached to different atoms, aren't they? The red one is attached to an oxygen and the blue one is attached to a carbon. And so based on atom, and since carbon and oxygen are in the same period, right, they're both second period elements, that means that the red hydrogen should be the most acidic hydrogen, right? If we draw the conjugate base, we should, the conjugate base of this molecule should be this, right? And the blue hydrogen should remain intact. And again, we base that off of atom, right? That's what we base it off of because, again, carbon and oxygen are in the same period. Remember, when you have two elements that are in the same group, we go off of atomic size, but here we go off of electronegativity. Anyhow, if you were to look up the pKa values of these two hydrogens, this one here has a pKa of around 10, and this one here has a pKa in the neighborhood of 40. Okay, even if I'm off by a couple log units, it's close enough, right? So you can clearly see that the that the hydrogen in red is much more acidic. Okay, let's move on to B. I'll just throw this out there to my students. Can anybody tell me which one of these hydrogens, the red or the blue, would be more acidic?
Red.
Yeah, absolutely, right? Now, if we look at the atoms that both of these hydrogens are attached to, they're both attached to carbon. So we can't use atom, can we? But if we go to the letter R, you can definitely use resonance to solve this one. So that's what we're going to use. We're going to use resonance, right? And if we drew the conjugate base that results from removal of the red proton, we're going to end up with this molecule, right? We're going to end up with this where we have a negative charge down here, and then we still have the blue proton, we still have the blue proton intact. And you should be aware that there are two resonance structures, right? I can draw a resonance structure with these two curved arrows for this conjugate base, and I can draw another resonance structure here, right? So there's two possible resonance structures for this conjugate base. Now, this is not correct, so don't write this down, and I'm going to erase it. But if you were to choose the blue proton, if you were to make a carbanion like this, yes, it has a resonance structure. Absolutely, this is resonance stabilized, but there's only one resonance structure. Whereas when we remove the red proton, we have two resonance contributors besides this carbanion right here. And so resonance is the deciding factor in this one. All right, if we look at C, C is very similar to the first one, to A, because the first hydrogen, the red one, is attached to an oxygen, and the other ones are attached to a nitrogen. Since, again, nitrogen and oxygen are in the same period, they're in the second period, you should know carbon, nitrogen, oxygen, fluorine, you should at least know that much, right? That comes up, these elements come up so often in organic chemistry, you know, you can fill in what you know from there, right? Since oxygen is more electronegative than nitrogen, in fact, oxygen is the second most electronegative element in the periodic table, that means the red hydrogen is going to be the most acidic. And so we could draw the conjugate base that results just for some practice, like this. There we go, like that. Put in our lone pair. And there we go. And so again, we used atom to solve that problem. So again, you need to familiarize yourself with the aereo concept, and it's also wise to familiarize yourself with pKa's. Just going back to this one here, because we discussed the pKa of both of these protons last lecture, the pKa of this proton in red is around 9, so the pKa of this is around 9, and then the pKa of this hydrogen is around 19. Okay, close enough. Anyhow, there we go. So we can use the qualitative method using the aereo method, which is, you know, designed by David Klein, I guess, or you can use just pKa values. And I recommend that you memorize the pKa values in table 3.1. Okay, well, let's talk about predicting the equilibrium position. And we discussed this at length during our last lecture, but let's talk about it even more. So if we have an acid-base reaction, and I mean, we're starting it with some kind of generic acid here, HA, that represents our acid. Here we have our base. Right here we have our conjugate base, and you should be able to label these. And here we have our conjugate acid, nothing new under the sun there. Well, you see that we have a set of equilibrium arrows here, and the question that we want to answer in section 3.5 is, which side does the equilibrium lie to? Meaning, is the equilibrium more like this? Is it heavier on the side of the products, or does the equilibrium lie more to the side of the reactants? And there's two ways that we can decide, where does the equilibrium lie? And the ways that we can do that are, number one, we can compare the pKa values of the acid and the conjugate acid, right? And the weaker acid is going to be favored. I discussed that last lecture. So we look for the acid or conjugate acid with the higher pKa, or we can also do it using Aereo, right? Looking at the relative stability of the bases, the base and the conjugate base, right? Whichever one is more stable, the equilibrium is going to lie to that side, right? If something's more stable, it's going to go in that direction, right? Anyhow, so let's look at some examples here, and we'll start with this one here. It says, predict the position of the equilibrium of the following reaction. Well, first, let's just do it using pKa values. So I want to see who's been practicing their pKa values. You guys know this molecule. It comes up Avogadro's number of times in General Chemistry 1, General Chemistry 2, Organic Chemistry. Who could name this molecule that I have circled in yellow?
Ammonia?
Absolutely, that's ammonia, just plain old ammonia. Does anybody memorize, or has anybody memorized the pKa of ammonia?
I believe it's 38.
Yeah, it's around 38. Even if you had been off by a couple of log units, trust me, you're probably almost always going to get the right answer in this class, right? So 38, I buy that. And then over here we have butane. Okay, so this is butane, the same butane found in a butane lighter. Butane is just a plain old hydrocarbon. Hydrocarbons have a pKa of around 50, so really high pKa. Okay, well, if we compare the relative pKa's, we know that the equilibrium is going to lie to the side of the weaker acid, right? The higher the pKa, the weaker the acid. Therefore, we can conclude that the equilibrium is going to lie to the right side. It's going to favor the products. That's all well and good, and we solved that, again, using pKa values. But let's say you had forgotten your pKa values. You just couldn't remember, maybe you forgot the pKa of butane, which hopefully you won't do. But let's say you wanted to use Aereo. Well, then you would compare the stability of the base, okay, versus the stability or the relative stability of the conjugate base, right? The conjugate base, okay? They both have negative charges, and if we use Aereo, A-R-I-O, you can see that in this, son of a gun, what happened there? Here we go. Anyhow, so you can see that in the conjugate base, the negative charge is on a nitrogen, right? And nitrogen is more electronegative than carbon. Again, carbon and nitrogen are in the same period. And so, again, we predict that this is we know that this is the more stable base, and therefore, again, the equilibrium is going to lie to the right-hand side. So we can use both methods to justify, the fact that the equilibrium lies to the right. It lies to the side of the products. Okay, let me just give you another example before we move on. This is just, let me think here. Okay, let's say we had something like this, okay? And just give me a second here. So let's say we had this. No, I want to start it with phenol. Yeah, phenol plus hydroxide. Oops, it's kind of hard to see my electrons here. Okay, here we go. And then we'd have the phenoxide on this side. Here we go. And we got water over here. Okay, so here's another equilibrium. Okay, and I'm just going to ask you guys, could anybody solve this one and tell me which side the equilibrium would lie to? using either method? Yeah,
It would
okay.
favor the product side.
Absolutely it would, right? Now let's do it using area. Let's go backwards this time, okay? So if we were to solve this using area, we can't use A because the negative charge here is on an oxygen, the negative charge here is on an oxygen. So we'll cross that off. When we get to R though, we can use resonance, can't we? Right? We can use resonance because this anion here has resonance structures, whereas this anion here doesn't. Right? So this is the more stable base, and therefore the equilibrium is going to lie to the side of the products, just like my students have said. Okay, it's going to lie. Byron says forward. I get what you mean. Yeah, it lies to the side of the products. Okay, well, we could do the exact same thing using pKa's, right? This molecule here, this is called phenol. Phenol has a pKa of around 10, okay, 9.9, whatever. And water has a pKa of 15.7. So which one of these is the weaker acid? Water is the weaker acid. And therefore, again, we predict that the equilibrium is going to lie to the side of the products. Okay, so that's the kind of rationale you want to use, and you can guarantee that I'm going to ask you some kind of questions like this on the quiz. You know, it's very easy for me to put this together. You know, which side does the equilibrium lie to, left or the right, right? Okay, let's talk about reagent choice here. And I just want to kind of discuss this kind of quickly with you. I kind of based this slide off of a question. It's question 3.29, and I'll tell you what I mean in a second here. It just says, another important skill is to be able to choose an appropriate reagent for an acid-base reaction. So what that means is if you're doing any kind of acid-base chemistry in the lab, okay, and you want to get your reaction to work, well, you're going to have to choose the appropriate reagents in order to do that, right? You'd have to choose appropriate reagents. Otherwise, you're just wasting chemicals and wasting time and wasting money, right? So it's skill that you have to have, is it says here, you've got to be able to choose an acid from table 3.1 that could effectively protonate each of the following molecules. Now, these are all ions, but anyhow, if we want to protonate these, I'll divide this up into 4 here like this. So we're going to look at 1, 2, 3, 4. Now, there's more than one answer to all of these, all right? But I just want to quickly go over them with you and just give you some examples of what would work. Let's say, for example, we'll start with this one here. This is called an acetylide ion. You don't need to know that now, but that's something you'll learn later on. If you were to treat that with water, right? If you were to put the acetylide ion in water, it will effectively protonate that. It's going to work to protonate that carbon with the negative charge. Let me prove it to you, because you're going to end up with this molecule, acetylene, which is an alkyne plus hydroxide. If we compare the relative pKa's of the acid, in this case, which would be the water, which is 15.7, and the conjugate acid, which is the acetylene, which has a pKa of 25, again, you can see there's a difference of almost 10 log units. And so, as I told you last class, I said the cutoff is kind of around 10. So that means that water is going to be effective at protonating acetylene. Okay, this ion over here, this is a carbanion of acetone. Anyhow, same rationale. What would be a good acid to protonate this? Well, let me give you an example. And again, there's more than one answer for this. But if we were to try to quench this or to protonate this with hydronium, right, you should have memorized that the pK of hydronium is minus 1.7, even minus 2 will do. Well, if you protonate that, you end up with a ketone. This is acetone, and we looked at the pK of this in the last class. It's 19. And so the conjugate base that would be left over would be water. And so we compare our acid and our conjugate acid. And you look at the equilibrium, and it's going to lie to the side of the weaker acid. Same thing. So hydronium would be an appropriate choice. Okay, let's go down to this one, because now we've got the acetone molecule intact. How would we protonate that? Right? Let's do something that might not work. You know, if we were to put that in hydronium, right? If we were to add H3O plus to that, is it going to work? You know, is it going to, maybe I should just put an arrow like this. Is it going to work? Is it going to effectively protonate this oxygen? Well, let's take a look. If we draw the conjugate acid that results, and we looked at the pK of this in the last class. It's in the table 3.1. If you compare the relative pKa's, we have a pK of minus 1.7, but the pK of this protonated oxygen on a carbonyl is negative 7.3. And so that means that this is not going to work, right? If I put hydronium in with this molecule, I'm not going to get any of this. It's not going to work. It's not going to protonate it. So that means I need what? I need a stronger acid. So let's get a stronger acid going here. Let's see. What's a stronger acid? Hey, could somebody tell me an acid that's got a pKa lower than negative 7.3? There's really only one answer from our table, I think.
H2SO4.
Hot diggity darn, you're 100% right. Exactly, it's sulfuric acid. It's got a pK of what? Minus 9. So that's going to work. And you're saying, hey, Mr. Dion, look, it's only a difference of 1.7 log units. It might not, work that well. Well, the equilibrium is going to lie to the side of the protonated carbonyl. So the equilibrium will lie to the right. Okay? And then the last one, this is an acetate ion. So we're going to see acetate ions come up over and over in this class. And I just came up with another example of something that would work. So if you were to use HCl, and this is kind of a little practice of just, do we know our pKa's? Does anybody have the pK of HCl memorized?
Negative 7.
Hot diggity darn, man. Good class. Okay. So we'd end up with chloride, right? We have a carboxylic acid, which has a pK of around, I know the table says 4.75. We'll just put 5. Okay, so you can see that the equilibrium is going to lie hard to the side of the carboxylic acid because we have a difference of what, 12 log units. Okay, anyhow, that's just the kind of rationale. And the reason I put this, and I never take this out of my slides, is because I just like to do a little pK practice with my students. But the bottom line is that the acid that you choose to protonate, okay, to protonate these anions, or neutral compound in the case of acetone, but the acid has to be stronger than the conjugate acid that's formed, right? That's all it is. It's just got to be a stronger acid, okay? There we go. So something you want to think about, and I know a lot of you are enrolled in 3102, and these are the kind of thought processes you want to have when you step into a lab, okay? You want to make sure you're not wasting reagents. All right. Well, let's talk about wasting reagents anymore and talk about what's called the leveling effect, and how I'm going to show you an example of how you could waste reagents and botch a reaction, which is something that you don't want to do. Anyhow, the leveling effect. And the leveling effect, you might not have heard the term leveling effect before, but I guarantee you that you've seen the leveling effect in action, okay? Because you've all passed general chemistry too, so you've definitely seen the leveling effect. And here it is. It says another important skill is to be able to choose an appropriate solvent for an acid-base reaction. And if you've looked at the slides, you'll notice that there's more slides about the leveling effect than there was about the predicting equilibrium. It's because it's really important that not only can you set up a reaction, but you've got to have it in solution. Most of the reactions that we look at, virtually all of them in organic chemistry, are done in solution. So if you don't have an appropriate solvent, your reaction's not going to work. And you have to know solvents, all right? Something that you don't talk about a whole heck of a lot in general chemistry. Well, let's think about it. It says the solvent should be able to surround the reactants, okay, and facilitate their collisions, right? Think about Gen Chem 2, collision theory, okay, but it can't react. The solvent is not, you don't want the solvent to react with any of the reactants. You just want it to play a role of solubilizing everything and providing an environment where reactants can collide and do what they're supposed to do to get the products that you want. Now let's talk about water. Now, you know that water can act as an acid or a base, depending on the situation. And so it has a leveling effect on strong acids and bases. Let me explain what I mean. It says the acid stronger than hydronium cannot be used in water. And if you're like, well, that's not true, Mr. Dion. You can put sulfuric acid in water. You can do that. And I'd say, yeah, you're right, you can. But what do you have in solution? Let me show you, okay? What you've got, okay, if you take sulfuric acid, strong acid, pK of -9, and you put that in water, right? You don't have any sulfuric acid, right? You've got very little sulfuric acid. Mostly what you have is hydronium and the hydrogen sulfate anion. Right, let me prove it to you. If the pK of this is -9 and the pK of this, pKa, is -1.7, that means that mostly in solution you've got this. You don't have a lot of sulfuric acid left over. Okay, I get it. You know, if I put a strong acid in water, I'm mostly going to have hydronium. It also says that base is stronger than hydroxide cannot be used in water. Now, I have explanations for all of these, or these 2 points on the next slide. So I'm going to skip ahead here, and let me show you the acid thing with a different example. Okay, this is a different example here. It says appropriate use for water as a solvent is when the base, the conjugate base, is not stronger, or the base, sorry, is not stronger than hydroxide. So here is the acetate ion. So here's acetate. Okay, and you don't need to have acetate memorized for the quiz. I just like to say the names of things that we're going to see literally hundreds and hundreds of times. So by the time we get there, you'll be like, hey, I remember that. You know, I've seen that so many times. So we have the acetate ion, and if we put that in water, which side does the equilibrium lie to? Well, the equilibrium is going to lie to the left-hand side, right? Because water has a much higher pKa than acetic acid. So this is acetic acid over here. All right. So what it's saying here in this bullet point is that water is an appropriate solvent for an acetate ion. Right? If you take an acetate ion and you dissolve it in water, you still have your acetate ion. It didn't go away. You didn't ruin it. Okay. So it says here, with water as a solvent, the acetate ion will react with the water. Some, yes, it will. Of course, it's going to. But the equilibrium is going to greatly favor the left side. And so water is an appropriate choice. So let's say you do a reaction in organic chemistry where you use acetate. Happens all the time. Would water be appropriate? The answer is yes. It would be a good choice. Nothing wrong with that at all. I give you, 100%. Well, let's look at that example that I showed you earlier on. Again, we know that water is amphoteric, meaning it can behave as an acid and a base. And here's what happens when we take water and we put it in a strong acid like HCl or H2SO4. You can view those solutions of sulfuric acid and hydrochloric acid as just an aqueous solution of hydronium, right? Because sulfuric acid or hydrochloric acid are so strong that they're effectively going to generate just hydronium, right? The equilibrium is going to lie hard to this side here. Now, the difference between concentrated and dilute sulfuric acid is just the concentration of hydronium in the solution. Okay. Now, I know that some of you have probably thought about this many times, and some of you maybe not. So give me a thumbs up if you just follow me on the concept, like, yeah, I get it. We looked at pKa's long enough that I think I understand why the equilibrium would lie to the right side in this case. All right, good. Might be a concept that you have to take some time and read and look at it in a little bit more detail and practice it a little more. But I want to give you a good example here to help us understand the leveling effect. Okay, so here's the question. If you look at this reaction right here, we have an alkyne. Okay, this is called amide. The this is dimethylamide. Anyhow, because these are both methyl groups here. Anyhow, but we have a strong base. Okay, and then we form this acetylide derivative or alkylide derivative here. Anyhow, my question to you is this: nothing more than this. You see this beautiful reaction down here? Well, you have a reaction arrow, and normally in organic chemistry, we write the solvent on top of the arrow. Okay, so we write it above the arrow. My question to you is, if I was to try to do this reaction in water or hexane. So hexane is 1, 2, 3, 4, 5, 6 carbons like this. So it's just a hydrocarbon. Which one of these would be an appropriate solvent to do this reaction? Okay, just imagine it this way. Somebody, you got a job, you work in a lab, and somebody says, you know what, I'm going to give you a $10,000 bonus if you can do this reaction, right? All you've got to do is choose the appropriate solvent. Is it water or is it hexane? Let's think about what would happen if you were to run this reaction in water, okay? What are the reactants? This side represents the reactants, okay? So you went to the reagent cupboard and you picked out this alkyne and you picked out this base, okay? You take them, you weigh them out on a balance. Great, you've done that. Then you put them in water. What happens? Well, the water is not going to react with the alkyne. There's not going to be any reaction there. There's nothing basic enough to rip off a proton with water. But we have a base here, don't we? So what kind of reaction would occur between this anion here and water? Just because I don't have a lot of space, I'm going to write it up here. Let's do it. If we had that base, okay, plus H2O, what's going to happen? Is that base going to deprotonate? Is that base going to deprotonate the water and form hydroxide? Which side is the equilibrium going to lie to? Well, let's investigate. We know that water is behaving as an acid here. Its pKa is 15.7, and this is an amine. And we said that amines have a pKa of around 36, 38, somewhere in that neighborhood, right? Let me just write it down here, the number. So we'll say 37, okay? Even if I'm off by a little bit, doesn't matter, because the difference between these numbers is, greater than 19. That's big. That's 10 to the power of 19. So that tells us that the equilibrium is going to lie, and I'm going to erase these arrows, the equilibrium is going to lie hard to this side, right? So that means that if you were to try this reaction for the $10,000 bonus and you were to put it in water, what's going to happen is you're going to destroy that. Okay, now you don't destroy matter, I'm not saying that, but you're only going to end up with the amine. Your base will be gone. Base is gone to base heaven. Okay, it's gone. Give me a thumbs up if you just follow me, like, yeah, I get it. If I was to dump these two reactants in water, it's not going to work, right? I'm in trouble. I've just ruined everything. Great, thanks, Moira. Perfect. Well, what if we tried the reaction in hexane? Will this base react with hexane? Let's draw it down here. If we had our base, here we go. Okay, and we put it in hexane. 1, 2, 3, 4, 5, 6, like that. Okay, is it going to deprotonate it? Now, there's all manner of things that you could draw here, but we'll just draw the deprotonated hexane. So 1, 2, 3, 4, 5, 6, and we removed a proton like this, and then we'll put plus plus this guy here. Okay, and this is supposed to be an equilibrium arrow, isn't it? Here we go. Okay, so the question is, which side is it going to lie to? Let's evaluate the pKa's. Here's our acid. It's got a pKa of 50. Here's our conjugate acid. It's got a pKa of 38. The equilibrium is going to lie hard to this side, right? Because you have a difference of 50 minus 38. That's 10 to the power of 12. That's a huge difference, right? So that means that if you were to take these two reactants and put them in hexane, you're safe, right? You're still going to have these two things intact. Give me a thumbs up if you're like, hot diggity Darren, throw me in the lab. I'm ready. I'm ready. Just give me some reagents, Mr. Dion, and just give me a cupboard full of solvents, and I'll choose the right one. I know I spent a bit of time explaining that, but I want to make sure that you're with me on the leveling effect. It's so important. It's just something that comes up a lot, and we don't really address it a ton moving forward in the class. So I just want you to understand why we're so hung up on solvents. Something you're going to see even more in organic chemistry too, and you will see it in this class too, is not only are we going to learn reactions, but we're going to learn the solvents that you do the reactions in. Okay, and sometimes students will get frustrated and say, I know the reaction, why do I have to know the solvent too? And the reason why is because solvents play a pivotal role, right? If you choose the wrong solvent, you can ruin a reaction. Now, I worked in industry most of my adult life, and you might be wondering, Mr. Dion, did you ever choose the wrong solvent? You studied organic chemistry, and the answer is everybody's chosen the wrong solvent at one time in their life. Oh, okay, anyhow, let's move on to section 3.7. Let's compare these two alcohols here. We're really switching gears. We do that a lot in Organic Chemistry 1, especially in the first half. If you look at these two beautiful alcohols here, you've got tert-butanol and ethanol, and you're like, yeah, that's the same ethanol in Coors Light. Yeah, absolutely. Okay, if we compare these two alcohols, you just have a plain old alcohol. Why would the difference in pKa be so great? Right? It's a difference of 2 log units. That's a difference of 10 to the power of 2. That means that ethanol is 100 times more acidic than tert-butanol. You're like, 100 times, that's quite a bit. Why would it be? And the thing is, we can't use areo to explain it. It doesn't work. We can't use atom because of conjugate base. Both of the negative charges would be on an oxygen. You can't use resonance. You can't use induction, and you can't use orbital, right? None of these work. Well, the answer must be based on the title, which is Solvating Effects, okay? And it says here at the very bottom, we're still talking about solvents, the ability of a solvent to stabilize a conjugate base comes into play in this specific example. So if we think about the conjugate bases, right? So this is just the conjugate base. I don't know why they didn't put the negative charge in. How about I do it for you? So here's a negative charge here. So the negative charge, or sorry, the conjugate base of tert-butanol is called tert-butoxide, and the conjugate base of ethanol is called ethoxide. Anyhow, if you look at these two, what's going to stabilize the negative charge, right? What stabilizes it? Well, it's the solvent. It's the environment that it's in, right? The solvent is going to interact with that anion, and the solvent is going to stabilize it. Now, it could be through a dipole interaction, right? It could be through a hydrogen bond, but regardless, the solvent is going to stabilize it. Now, the answer to the question, why is ethanol 100 times more acidic than tert-butanol, is simply this. It's based off of the size of this group right here. Now, it doesn't look very big because it looks like 3 sticks, but I promise you, if you make a molecular model of this, this is 3 CH3 groups, right? This is 3 methyl groups. Now, hold on. If we draw those out as structural formulas, right, you've got CH3, you've got CH3, so on and so forth, and that's shown down here in this space-filling model. And so the answer is that you can't get as many solvent molecules around that negative charge to stabilize it. In ethoxide, you've only got 1 CH3. You do have free rotation around this bond, but it's not as sterically hindered, and so you can get more solvent molecules around that negative charge to stabilize it, and that's all there is to it. Okay, that's the answer. It's a very specific case that he brings up in this book, but it is an important case, and you know, even my brother has to admit, you know, organic chemistry is logical, right? There's always a logical explanation for just about everything in organic chemistry. All right, let's move on again to section 3.8, which is counterions. You can see that I only have one slide on this whole section. It's a very short section, but it addresses something that you probably called spectator ions in General Chemistry 1 and General Chemistry 2. In case you didn't notice, I mean, if we were to go back in the slides here, I don't know, where would we go? Even just look here. Did anybody notice this, that I keep drawing negative charges? And you're like, Mr. Dion, you can't have a solution that's negatively charged. There's no such thing, right? You'd be 100% correct, right? Yeah. And then there's other examples here, right? Any of these? No, not those. Those are all filled up. But anyhow, yeah, here we have a negative charge overall here. Here we have a negative charge here. So if any of you are wondering, like, what the heck, Mr. Dion, there's no such thing as a negatively charged solution that doesn't exist, you would be 100% correct. There is no such thing as a negatively charged solution. So then you might start asking yourself, scratching your head and saying, where's the cation? Where's the sodium or the lithium or the potassium? Aren't those still elements? Yeah, and the answer is absolutely they are. But they're always present, and we need them to balance the overall charge of a solution. But here's the answer. In organic chemistry, we usually just leave them out. Okay. Now, in general chemistry, you were used to seeing reactions like this all the time, where you included all the spectator ions. But in organic chemistry, oftentimes we just leave them out. Okay. And the reason why and if you're like, well, that makes it more complicated. I thought this was an introductory organic chemistry class. It is. And the bottom line is that 98% of the reactions that you'll study in organic chemistry 1 and organic chemistry 2, the cation doesn't even play a role. Okay, so you don't have to stress about it, right? We just leave it out, maybe 95% of the time. There's a very few exceptions of reactions that we will look at in this class where the cation is going to play a role. I will totally walk you through it and explain why the cation plays a role, but most of the time it doesn't. Okay, so there's nothing wrong. It is totally acceptable in organic chemistry to write this reaction and to leave it out. If you want to write in, you know, a cation here, if that helps you out, okay, right, that's totally fine. Now, if you're wondering, is it always a sodium? No, not necessarily. And again, that's why we leave it out. It doesn't matter. Okay, it doesn't affect the reaction. When you see OH minus in organic chemistry, it might be sodium hydroxide, it might be lithium hydroxide, it might be potassium hydroxide, whatever. They're all commonly used bases. But the bottom line is, most often we're going to leave counterions out. All right, there you go. That covers all section 3.8. And this brings us to the very last section of chapter 3. And depending on where you took General Chemistry 2 or who your instructor was, you've probably heard of acids and bases. If you go all the way back to the first slide that I presented last class, the first thing I talked about was Arrhenius. was the Arrhenius definition of an acid and a base, right? I said the Arrhenius definition of an acid is something that donates a proton, H+, and the Arrhenius definition of a base is something that donates hydroxide, OH-. Okay, and I said, well, that didn't answer why ammonia behaves as a base or is basic. And I said, well, then Bronsted-Lowry came along and then they broadened the definition and they said that an acid is a proton donor and a base is a proton acceptor. We've spent quite a bit of time on that. But there are other acids and bases that don't fit the Bronsted-Lowry definition. And so to broaden it even more, Lewis came along, Gilbert Lewis, and he developed Lewis acid-base theory. And so here's the definition of a Lewis acid and a Lewis base. A Lewis acid is an electron acceptor, and a Lewis base is an electron donor. All right, it's easy to remember because you have acid acceptor, both start with the letter A, and you have B and D. You know, I don't know. They're more closely related than B and A, I guess. Anyhow, there you go. So an acid accepts electrons, a Lewis acid, and a Lewis base donates electrons. Now, if you're like, well, when do I apply Lewis acid-base theory? Well, if you look at every single acid-base reaction that we've looked at in this entire chapter, everything that I labeled an acid was a Lewis acid, and everything that I labeled a base was a Lewis base as well. But sometimes we need to invoke Lewis acid-base theory to help us understand, right? Sometimes Bronsted-Lowry doesn't cut the mustard. Now, if we look at this example here, right, we have water behaving as our base. Now I'm just talking about Bronsted-Lowry here, right? Okay, because it's accepting a proton. We have our acid here, Bronsted-Lowry, right? It's donating a proton. Okay, good. We have our conjugate acid over here, and then we have our conjugate base. Now I just used Bronsted-Lowry to analyze that, but let's think about it in terms of Lewis acid base. Well, look at our base. What's it doing? It's donating a pair of electrons. A Lewis base is an electron donor, electron pair donor. What's our acid doing? It's accepting a pair of electrons, right, by this curved arrow. And so a Lewis acid is an electron pair acceptor. And so you see how even though we can label something a Bronsted acid or a Bronsted base, the Lewis acid base concept still fits. Now, if you're wondering, give me an example of where you could only use Lewis acid base theory, and that would be something like this one here. Okay, we have a reaction between water and boron trifluoride, and you see how water is donating a pair of electrons to the boron trifluoride to make this compound here that we call a Zwitter ion. Okay, Zwitter ion, good German word, right? To a positive and a negative charge in the same molecule. Overall, it's neutral. Could anybody tell me, is water behaving as the Lewis acid or the Lewis base here?
A Lewis base?
Absolutely, yeah. This is our Lewis base, right? Because it's donating the pair of electrons, and this is our Lewis acid, because it's accepting the pair of electrons, and nothing more than that. So Lewis acid and Lewis base. Now you can imagine I'm going to ask you some questions about this on your next quiz. So let's think about Lewis acids and Lewis bases. Let's write down what we know. We know that a Lewis acid is an electron acceptor. Okay, and we know that a Lewis base is an electron donor. All right, so we've got some cheat notes there. Now we can take a look at these two problems. I'll let you look at them for a second here, and then we'll come back and we'll answer them. I'm just going to get a drink of water. All right, now that you've had a chance to look at the first one, could anybody tell me, and if I label, I don't need to label these, you can name the second compound. Could anybody tell me which one of these is the Lewis acid? Yeah, exactly, the aluminum chloride, right? This is the, let me get a different colored pen. This is the Lewis acid, and this is our Lewis base. Not giving credit to Lewis. There we go, Lewis base. And you should be able to draw the curved arrows for this, right? We have the base donating a pair of electrons to the aluminum, like that. Okay, so Lewis acid and Lewis base. If we look at the example on the bottom, we could start by drawing the curved arrows if you want. You know, you could practice your curved arrow mechanism drawing, right? We're going to donate a pair of electrons from here, and this is going to accept a pair of electrons. So could anybody tell me which one of these will be the Lewis acid? Yeah, H3O plus, right? This is the Lewis acid, and this is the Lewis base. Why is this ketone the Lewis base? Because it's donating a pair of electrons. Why is hydronium the Lewis acid? Because it's accepting this pair of electrons, right? And if you need to draw in all your lone pairs, there's many lone pairs missing on this slide, aren't there? Right? Piles of them. All the lone pairs on the chlorines aren't drawn. Okay, and I took these directly from our textbook. Right? They leave out lone pairs all the time, so you could fill all those in. Right? Chlorine always has one bond. And 3 lone pairs, the water, we're missing the pair there, we're missing a pair here. Now we've got them all filled in, right? Okay, there we go. And that covers all of the content, I believe, for chapter 3, acids and bases.